Hi Manish, yes, the recording is on. Please take it away.
Yeah, Hi everybody. Today we will discuss about this firmware update design topic. Uh, Thanks for joining this meeting. So let me start with the agenda. What we are going to cover today. We will see the firmware update current scenarios in the ARM platform, how exactly it is working. Then we will go through basically the specification of the PSA firmware update, uh, and I will give the overview what it exactly mention about how the firmware update flow should work in the standard way. There are two cases we will cover over there. Like I will give a broad overview of that, like when the flash is present in the secure world and when flash is basically controlled by the non-secure world. Then I will talk a little bit more about the metadata, what are the metadata fields are present and how these fields are getting updated and how TFA use these fields in order to decide where the firmware update resides. And then we will go through the ABIs like between the two that mention the calling between the update client and update agent. These are like FFA ABIs. We will look into that when I come to that slide. And then what are the things we covered from the TFA? So this is the major things like I want to cover in this presentation, like from the TFA perspective, what are the things are completed or what are the things are in review, and then what are the tests we have executed till now, the unit tested, and what are the integration tests are planned. So we'll go through this flow. So how the firmware update current scenario right now, which is kind of very much recovery kind of mechanism, and uh, this recovery mechanism, uh, we don't call it as a kind of we call it as a firmware update, but it is really a recovery thing. So we have a test case in the TFA test to corrupt the TOC header and then corrupt the BL2 image. That basically lands in that basically get detected in the BL1. If you can see over here, that is the first component running from the immutable. And then once that get detected, then we will start the firmware update flow. So the BL1 will load all the necessary components which are needed in order to achieve the firmware recovery. So it will load the BL1U component, which runs in the non-secure world. And then the non-secure world will talk to the BL1 over the SMC calls and then load the subsequent components which are needed in order to do the recovery. So we generally load the BL2U component. BL2U component needed in order to enable DRAM for the non-secure world, and we just execute BL2U component, and then that initialize the DRAM and give the and initialize and give the control to the non-secure world so that non-secure world can do the further flashing procedure. Once the BL2U execution gets done, then BL1U component load, non-secure BL1U component loads the non-secure BL2U component, which this component basically do the job of actual recovery. Now we have the DRAM. Now the non-secure world have the DRAM access, which it can use to stage the firmware update. So BL2U's main job is to uh, get the backup image from which is present in the flash at particular location, then stage it into the DRAM, and uh, then that staged image eventually flash into the corrupted partition present into the flash, and that's how the recovery gets done. This is how we have it till now, and we call it as a recovery things. This is not actual firmware update. It is just a way to uh, do the uh, do the recovery and get the firmware back. Uh, this is how the ARM platform defines the recovery mechanism, but other platforms can have their own mechanism to do the recovery. And there is no standard way for the recovery mechanism across the platforms. So uh, we thought of making the we thought of changing this from recovery to the firmware update and making it more into the standard way. uh, so let's see in general how the firmware update generally works. So in general, all the firmwares which are getting developed are getting submitted to this firmware store, which we call as a firmware build. And then the device management system will take this firmware from this store and uh, do the sanity checking of those firmwares and then send those firmwares over the cloud. And then those firmware finally will get downloaded into the devices. So the specification which we developed basically talks more related to the uh, how the software should work inside the device, and how finally that software will eventually write this firmware update received into the non-volatile storage area. So let's see in the further diagram uh, uh, what are the components we have defined in the specification and how these components plays role in doing the firmware update. So as I shown in the last diagram, we have a device. There is some software is running inside the device. Uh, the firmware update specification uh, 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 introduce the two terminologies like update client and update agent. Update client basically takes the new firmware from the external world and then pass that firmware to the update agent. And update agent will be having the flash driver present over there, which eventually will write that firmware into the non-volatile storage. So now the update client should have the access of the new should have access for the new firmware, which generally runs in the non-secure world, and it is a part of OS, and it takes the firmware, stage it, and then send it to the update agent. So update client location is almost fixed. It runs in the non-secure world, but update agent, it can lie in either non-secure world or it will be in the secure world. So we'll see in the further diagram the placement of update agent and how the flow will be. So uh, when we have the flash present in the secure side, then update agent lies into the secure side because then the flash can only controlled by the update agent. So the client is, as I mentioned, like it lies in the non-secure world. It is kind of OS. It receives the firmware, then it establishes the channel with the update agent, and then uh, I will talk these ABIs further. How via ABIs we will send this firmware to this update agent, and then update agent is stage this image, give it to the another trusted uh, application, which is either another trusted application or maybe it may be having its own flash driver and directly flash those images into the bank present in the non-volatile storage. So we have banking concept over here, which again the firmware update specification says the here the bank means it is a collection of the images, like and each bank should have the exact same number of images. So in considering the ARM platform, we have only the one image, which is the FIP image, which inside contains the different images, uh, and and the FIP version 1 should be present in first bank, and FIP version later version or updated version will be present in another bank. So at one point of time, there is only one active bank. We call it as active bank, the bank which basically used to run basically the TFA takes all the soft firmwares from that bank. And we call another bank as a update bank, which generally used by the update agent to update it. So if you can see here, like bank one is getting updated right now. So it is the updatable bank, and bank zero is nothing, is an active bank where all the firmwares currently residing and the softwares inside these banks are currently running. There is one more partition is there, which we call it as a metadata, which that I will cover it in the next slide. This basically get updated by the update agent and then consumed by the TFA to know which bank should use to take the images and then load into the account. So this is the case when the client and updater both are in the non-secure world. So there is we are not developing any areas over here, like um, the OS can have its own flash driver and then write the images what are coming from the external world into this bank, and at the same time it should update the metadata also to reflect like this bank is getting updated, and then subsequently the TFA on the reboot will get to know to take this bank. We'll cover what is the metadata in more details in the later slide. So yeah, so this is what the firmware metadata looks like. We have different fields in the firmware metadata. We have CRC32 is the field which is basically uh, uh, used by the updated by the update agent by calculating the CRC of this whole firmware metadata, and and update agent will update this field, and then subsequently on the reboot the TFA will use the same field, and TFA also will calculate the CRC of this metadata and compare it, and if that comparison matches, then that integrity of this metadata passed and will will take the will trust on the fields which are present in this metadata. We don't do the authentication of this metadata. This is not the ask because the fields present in this metadata are not that critical. So let's go with one by one field present in this metadata. Like, this is the version field which we have it currently, the first version of the metadata. It will get updated according to the new fields get added into the metadata. This active index is nothing but the index with which the firmware is currently running. The previous active index is nothing but the index which ran properly, which ran last properly. So I will show how the previous active index and active index plays the role in the next diagram. So it will be more clear. And it has the another field like image entries, like, and image entries will have um, the number of the images. So in ARM platform, we have only one image that as I mentioned, we have only FIP image, which is a clubbing of all the images. And we will specify its properties over here, like what is the type UUID of the FIP, where exactly in the, whether it is located in the flash SB-RAM. So accordingly, we'll update its UUID, and what are the and and depend upon the banks, like where exactly this FIP is located. Uh, the FIP's image UUID, that is a universal UUID. Like as I mentioned over here, so FIP1 is residing in bank 0 and FIP2 is residing in bank 1. So it may have the different UUIDs. So it mentions about that, like there will be, if there are two banks, then there will be two different structures like this, and with a different UUIDs mentioned. The accepted flag is here to mention like this particular FIP image is accepted and we can trust on that image. How this accepted flag works, yeah, again, I will show in the later diagram, so it will be more clear. So the firmware update specification uh, uh, mainly talks about the update client present in the non-secure world and update agent present in the secure world, and to communicate between update client and update agent. These are the ABIs are developed in the specification. So if you see in the left hand side figure over here and consider these are the initial fields where active index is 0. Active index is 0 is nothing but I am running with the bank 0, and update index is 1 is nothing but the index 1 is getting updated now. So once we get a new, once update client get a new firmware, then it will send a call to start the staging to the update agent, and update agent will use this these ABIs like FW open and FW sorry, update client will use these APIs to write send those images to the update agent, and update agent uh, will finally flash that particular images to this particular bank, that is bank one. And uh, once this staging get completed, then the active now the bank is updated with the new images what we have received by the update agent in the staging stage. So once this is done, then client again send the call to update agent to end the staging. And once the staging once the staging ends, then we update the active index to 1 because bank 1 gets updated. So now subsequent reboot, the active index equal to 1 is get used by the TFA for the authentication purpose. And the update index we switch back to the 0, so that next time when the update comes, it will write into the bank 0. And what the update index which was sorry, the active index which was 0 previously, that we write it into the previous active index because with that we were running properly. Uh, is there any question till now in this diagram? Okay, so let me go ahead. So once this trial run, now we are in the trial run and we are now trying the now the image is updated into the flash, and that is in the bank 1. So once the reboot happen, then the TFA will come into the picture. TFA will take this active index 1. It will retrieve all the images present into this active index, and then it will load the images from this active index and to the RAM, do the authentication, normal authentication process, and then again come back to the normal world, to the update client, uh, telling like this active index is working properly. once the authentication passed by the TFA, then client again runs some check on this bank, like whether the images are present in this bank are proper or not, by doing some sanity check, maybe by uh, initializing some drivers, checking their inits are working correctly or not. Once everything works, then update client will send FW accept image call to the update agent, and then this accepted flag will get true, and now we can trust on this image like it is working. So once this accepted flag becomes 1, then on the subsequent reboot, the TFA will so in the trial run, the TFA will not do the NV counter update because that time the accepted flag was 0. And once this accepted flag becomes 1 and reboot happen, then TFA will do the normal NV counter update if the NV counter value present in the certificate is higher than the value present in the platform NV counter. So and this clause is go on then. Are there any questions again on this diagram? I can move that. Okay.
Just verifying with you, Manish, that audio is working. So you can hear me, you should be able to hear everybody else. So.
Yeah.
Thank you.
Manish, just one question. Can I?
Yeah.
Well, you said like the client is the one which will be interacting with the external world to receive the firmware images, and then the agent will be the one which will be taking the data from this client. So, well, I mean, do this update agent is a secure entity or both or non-secure entities itself here? I mean,
no, here update agent is running in the secure world.
Okay.
And these ABIs are used to communicate with the update agent, which is so these ABIs to communicate from the non-secure world to secure world via FFA mechanism. So these are all the FFA calls to communicate with the update.
Okay, so all these steps are happening inside the secure world now. So once the image has been picked from the client, the communication between the client and the agent is happening securely.
Yeah, correct. So yeah, everything will be happen securely because means it will send the image, but the cache which is present in the cache is controlled by the secure side only. So update client cannot write anything directly. So we can avoid the malicious attacks in that case. And this will be the secure way to update from the secure side.
Okay, thank you.
Yeah. So what is the TFA bootloader general? So BL1 we have. So here is one assumption, like BL1 is always kind of immutable component, and we don't. So we have not also, and BL2. That's why the BL2 is not the updatable part of the specification. So BL1 always load the BL2 from some fixed address, and the BL2 onwards, what are the images are there are getting loaded from this loaded from any of this particular bank which update agent updates it. So we need this is whole things happen using the GPT parser. So all these just show the GPT image, it will be more clear then. So here if you see like FIP-A and FIP-B, these two images are like present in bank 1 and bank 0 and bank 1. So consider the FIPB is getting updated by the update agent. Then TFA will take this FIPB by reading the metadata. So metadata are also part of this GPT image. So all these things is a part of GPT image with the partition information present inside this partition table. So GPT is kind of recommended by the firmware update specification so that we can load the images. Uh, uh, we can have the UID of the every image, and this UID will be used by the parser to grab the images. So so this GPT parser support is enabled in the TFA bootloader to now to grab the images present in that GPT image. And as I mentioned, the CRC32 field in the metadata is uh, updated by the update agent. But again, TFA need to do the calculation of the CRC32 in TFA side also to match this CRC32 value with the field present over here, uh, updated by the update agent to check the integrity. So we have added the hardware and software, both the CRC32 support in the TFA. The hardware CRC32 support is basically recommended like if we have the ARM v8.0 platform onwards, where the hardware CRC32 field is hardware CRC32 is by default enabled. So we developed this software CRC32 basically use the zlib library where the CRC32 files are present. We are making use of it, and we are compiling that zlib as a part of build system. But software CRC32 is not recommended. If we are using the ARM v8 previous platform, then people still can add that support. And we have loading and parsing of the firmware update metadata. Again, using the GPT parsing, we will load the firmware metadata into some particular area in the RAM, and then then these all fields can be used in order to grab the images from the flash. So once this firmware metadata get updated, then PFA will read this active index present in this firmware update metadata, and then accordingly grab the image present in this GPT image. So, and we avoid the NV counter update in the trial run state. Trial run state is nothing but when the accepted flag is 0, that time we don't allow NV counter update, and that implementation is also present in the PFA. So let's look into the whole loop flow what I mentioned over here. So once we start at a BL2 entry point, we will call BL2 main as usual, and then we do the FW init function. So FW init function will is present in the FW driver. This function in turn called the FW metadata load. So FW metadata load will load this metadata present in the GPT image and load it into some structure in some global variables maybe, and then we do the sanity check of that firmware metadata whether all the fields are within bounded limit or not. And then, as I mentioned, we do the CRC32 validation of that loaded metadata. If this metadata failed, there are two metadatas are present, like here I mentioned we have two metadatas. One is if one failed, then we can always go to the backup metadata over here. So this is the fallback mechanism given. Once we once if there is some corruption in the primary metadata, then go to the backup metadata. It is exactly the same replica of the primary metadata, but just uh, just to uh, avoid if any problem comes in the primary metadata because of aging or anything, like somebody corrupted that metadata, then uh, we have the another metadata available. And if that also fails with the our CRC check or sanity check, then we go to the panic, or it is again like implementation defined. Either we can do a panic or we can go to the recovery mechanism. This is per platform decision. So during the firmware update data load, we developed one API, platform API, which set the metadata image source. So this metadata is actually uh, this metadata we want to set the IO policies first, so that the IO driver will get to know where this metadata is residing, and accordingly will take the action of the loading. So GPT is recommended. So ARM platform is using the GPT to grab the information where the metadata resides in the GPT, and accordingly update these IO policies. But if somebody don't want to go to the GPT, they can still update, they can still use this call and develop their method and update the location. IO policy is nothing but the location where exactly this firmware metadata is residing. And then IO driver will use this policy to load the images into the SRAM or DRAM as per the platform. So same thing we are doing for the all the FW images source. So in case of ARM platform, we have only one image source right now, that is I mentioned is the FIP. So again, for whether I need to take the FIP, first FIP or second FIP over here, if we have only the two banks, it get decided by the active firmware bank index. So I read this. So generally TFA read this metadata and get the active firmware bank index, and then accordingly update the location, update the IO policies for this firmware update image source. So in ARM platform, it is nothing but the FIP image source. So if it is active bank index, suppose it is 0, then I go ahead with the FIP first partition. If it is 1, then I will go ahead with the FIPB partition. So these two APIs are quite platform specific, and it is again depend upon whether the platform is having the GPT support or not. So and it just means to update the IO policy, means where the things are residing, so that the IO driver can understand properly and do the action of loading into the SRAM or DRAM accordingly. And this is nothing but this is the trial run detection. So once we get the once we start loading the images one by one present in this FIP, then we generally check whether the system is in the trial run. This gets checked with the help of that accepted flag in the metadata. If that accepted flag is 0, that means this image is not yet validated, and it is not yet agreed like it is a working image or not. And that's why we called it as a trial run. And if it is a trial run, then we don't do the action of the NV counter update. So this FW is trial run state. This method is developed already in the driver, and it is quite platform agnostic. Yeah, platform can call this method, and then if the platform is using this authentication driver, they don't need any action basically. This method will automatically get called, and accordingly, if it is a trial run, NV counter update get avoided, and if it is a regular run, the NV counter update get happen. So, this is how we have developed till now. We only take the active bank index and go ahead with that active bank and go ahead and take the images from that active bank index. But it may happen like that active bank index may be having some faulty images and may not go and pass the authentication check, or it may happen like at the normal world, these images are not working properly after the sanity check gets done by the update client. So we have this is upcoming now. This is not yet posted in the patch. So we generally start with this boot index with the active index, and we take the all the images from this active index. And then if the authentication get failed, then TFA itself will reboot, and then it will update some flag like uh, the authentication failure happened. And in the next reboot, this authentication failure get detected by BL2, and BL2 will then change this index to the previous active bank index.
So, one question, Manish, there.
Mhm.
How you are propagating this information over a reboot?
Yeah,
What?
so this is via persistent registers we are using. But this is yet to decide. Like so, reboot always happen like a warm reboot. So we are thinking this information will be called persistent across the reboot. So considering if the active index failed with the authentication, then we'll update some flag in the persistent register or in persistent memory somewhere, and that tells like the previous there is an error in the previous boot, and then we'll switch to the previous active index, and then we'll load all the images from the previous active index. And if this previous active index also fails the authentication, because this may not happen because previous active index is a proven one, like it was working previously, but it may happen like due to the aging effect of flash, some bits may get flip-flop and we may not pass the authentication. So there is a then then again we increment the count of that boot error code, and that incremented count then detected by BL2, and then it is a platform defined way to go to the recovery.
Yeah,
This
okay, okay.
mm, mm. and and suppose consider the case where the authentication passed for the active index and everything went well, but once the control goes to the normal world, some functionality may not be working and we are getting the continuous kind of watchdog reset. So this watchdog reset again get detected by the BL2, and we again try again with the same index for quite number of times. That's we call it maximum failed boots. So we try it for the certain amount of time, the same active index, and we'll see the whether the normal world drivers and software which is running gets recovered automatically or not. If it not recovered, then again after certain amount of trials, we go back to the previous active index, and we'll do the same things for the previous active index. And if that also fails, yeah, then we'll go to the recovery. So it is like for authentication, we take the decision immediately to go back to the previous active index, but for going back to the previous active index, once the control reach to the normal world, we do some retrials and then decide. Now consider active index is updated by the update agent, and it tells like all the new firmwares are lying in this active index. And but then TFA decide not to go with the active index and go with the previous active index. Then it becomes necessary to propagate that information to the update agent. So this is again like very much platform defined way to pass this whatever the boot index we derived to the update agent. It may be via some register, or it may be via some memory which is accessible by TF and TF update agent both. And then update agent accordingly once gets the information like active index and boot index is not equal, then it will update the active index with the boot index immediately, and the next reboot will happen properly with the active index. Any question till now? Sorry if I'm quite fast on this. Okay, so let me go ahead then. So what are the verification we have done till now? So as I mentioned, in GPT we have two FIPs, FIPB and FIP and FIPB, and again the two metadata over here. So these two metadatas, as I mentioned, one is both are kind of same metadata updated by the update agent and used by the TFA. The backup metadata is always like kind of redundant one, only get used for the fallback mechanism. And two FIPs in this means one is always active FIP and one is the updated FIP by the update agent. So to decide which to take, it's decided by reading this metadata. So we have created this metadata binary manually right now, as we don't have this full update client, update agent support yet. So we only created the manual binary with the two FIPs, with the two different versions of FIP present, and we created this metadata also manually, and we updated the field over there, calculated CRC using some shell utility and updated those metadata CRC values. So this is what I have shown over here. So this metadata is having some active index value with the proper CRC available in the CRC field. So once the device booted, the BL2 loads this metadata and do the CRC calculation, check the integrity of it, and see like whether to update the NV counter or not, depend upon the accepted flag present in the metadata, and which image to take, whether FIPA or FIPB, it's get decided depend upon that active index. So I just updated the active index to either A or either B, and then created the metadata images and added it over here, and then just check like whether I'm getting the proper image running or not. this whole implementation is right now posted externally, available in the trustedfirmware.org. Yeah, and with the documentation also updated for the platform API which we have developed till now. Yeah, this is already covered. Just to give a little bit more about the GPT, how exactly, maybe some partners already using the GPT concept, but till the 33 partitions, we have the partition table information, and from 34 onwards, we have the available partitions where we put all the partitions like FIPA, FIPB, these all are residing after 34, and its information like where exactly it start and end, that is present in this GPT header. The Jose who developed the specification, like developed some prototype code already for the QEMU platform, and with the U-boot and running STMM on top of Opti. This code, the TFA code for this is already, I think, available in the trustedfirmware.org. And just to, if anybody want to look at in that, how the, I think these patches need to be updated as per the latest update I have done. But anybody can go through this this implementation in the trustedfirmware.org and see how the QEMU platform works. So ongoing task, as I mentioned, like boot index decision, this is still pending, and we are looking for this persistent register support from the platform, and the pseudocode is already available, but yet the patch is not posted for this particular thing. And then the recovery flow, I'm thinking there will not be much changes. What we have, I shown in the first diagram, we always go ahead with that, but instead of the FIP, now we will be recovering the GPT over here. And GPT, the recovery indication flag accordingly, we need some changes over there. As I mentioned, we are not going immediately to recovery because we have always we have always a fallback partition present in the GPT, which we can rely on. And if that also not works, then we go to the recovery. So yeah, we do need some changes, and this will go along with this boot index decision changes. I guess. And the total compute team is already working on the update client and update agent flow. These patches are emerging right now. They have taken this full work which developed in the TFA, and at least they're able to now flash the they're able to develop the flash driver as a as a trusted application, and with this TFA patch tag, they're able to see like whether the firmware update switching is happening correctly or not.
One simple question is this one can be tested on QEMU, but when you have fresh update, you really want to see is there any new platform that we can verify this code?
You mean if it is a completely new platform, how we can?
Yeah. So do you have any physical platform that is can recommend it to us? We can port and modify the code and test it out.
Yeah, means you. If I understand your question, like you mean if it is a completely new platform, how we are going to update?
No,
no. I mean, is there like the church firmware has custom platforms, right? So ARM is not a real platform company. So do we have any custom platform or popular platform that you already implement this can show, so we can take it and just play around in addition to the QEMU, right?
Yeah. Okay. So the total compute platform is there where we are trying to develop the whole things that you can eventually use it, but I am not quite sure whether it is available publicly or not. But some things you can always check on the FVP platform, which is always available. Correct me, Joy, and I am wrong. Yeah.
FVP, total compute platform is public. This feature, the end-to-end feature, I am not sure whether it is there or not yet.
No, it will not be there.
But,
it will,
yeah. But total compute platform, to answer his question, total compute is a platform which is sort of a complete platform which will showcase all the features developed by ARM. So yes, you can keep an eye on total compute platforms.
So just to clarify again, so the total compute platform is a reference platform, but it's an emulated platform. So it's built using ARM's FVP technology that you can download from arm.com for various virtual emulated platforms. So it's equivalent to QEMU, and but it's the ARM mechanisms for.
Yeah. So my recommendation is maybe we need to eventually find some popular low-cost platform and porting this on it. Then people can verify, because firmware update is a very unique piece of software. It will not be very comfortable if you don't see the code actually write into the flash, right? And boot from the real platform. So that's my recommendation. So we need to make some kind of a low-cost platform available for people to play with.
So there is things like the Raspberry Pi ports for TFA, but it is up to the community to port the.
So public can discuss with Don, so see if the chat firmware can have some kind of platform implement this.
So just one note on this topic. I know that Linaro is working on implementing the end-to-end firmware update flow on an ST platform. And there's also some work on prototyping the end-to-end flow on an NXP IMX8MM. So this should be nearing the point where they can be publicly shared, and so when they're ready, we're happy to point you to these prototypes that run on physical platforms, and these platforms are also low cost, so it's easy to get a hold of them.
Yeah, thank you. I'm waiting that.
Any questions?
Hey Manish, I got a couple of questions. The first question is there any way the client knows that the update was successful, the client in the normal world? As the last, if I go to the spec in the setup phase, it says that update agent sends synchronous response to the client, signaling successful exchange of buffer. But I guess that's the last message. So that's the first one. Second is that it's being tested with Opti with STMM on it as an SP, right? So just curious if both upward and the downward communication is via FFA APIs in that case.
Yeah, I think this is used by with FFA only. Jose, correct me if I'm wrong. Like these all APIs are used for the means used from the U-boot to communicate with the STMM using the FFA calls. Is that correct?
Yes, that's correct. So the communication between U-boot or the client and the update agent is all conducted via FFA.
Okay, thanks. And the first question?
Sorry, can you repeat your question?
Sure. Is the client in the normal world, is there a way for him to know whether the update was successful or not?
Okay, so yeah, that specification is not developed. This is very much like up to the up to that OS which is running over there, or the software which is running in the normal world has to take care of it by doing some checks over there. But yeah, we don't have any APIs developed over here. Like, we can have directly a flash driver, and flash driver directly writes the data whatever is coming from the external side, and it will decide which bank to update, and accordingly update that bank, and then even calculate the metadata, CRC, and all those things. It has to be done by his own way, and then update the metadata. But there are no APIs are developed by specification. It's up to the platform.
There could be a use case which I was thinking where, the secure client gets interrupted while doing a firmware never gets serviced. So how does the non-secure world know about it?
Sure, no, this is I don't think so anything will be running when we are updating the firmware over here. Means if we have this case, then we are just rebooting, and then maybe the U-boot will be running here, will be slowly working just to update the things, and then we'll do the reboot. And nothing else will be running at that time.
Okay.
So I have one comment is if you are doing long time update, then secure update is very important. But if you are rebooting, right, I don't think it's that important, right? As long as we can update successfully update, the reliability of like you don't fail during the update is more important, because when you reboot it, you have a relative very secure environment, and that updated image will be checked, during boot anyway. So in general, I think when we reboot, we don't need to be overly complicated, right? We just make sure it can be reliably updated, don't cause any problem.
Okay, so there are two things, like means if the update agent can do the authentication and write the image into the bank, then then the reboot, I agree, then we don't need to do the authentication again because it has already been authenticated, or somebody can still do the authentication to just cross check like what are the things done by the update agent are correct or not. That way it will release some checks on the reboot. Is that answer your question? Is that what you mean?
Yeah, no, just a comment. So what I'm thinking is when you do firmware update in a newly booted environment, security is relative, not that important. It's already in a very secure environment. No matter if you are in the secure world or in non-secure world, the non-secure world is also very, very clear, right?
Okay, so
yeah. I think it's a little bit overkill.
But there will be some. This is why this is secure, because this is controlled only by the secure world, and any malicious attacks will not be possible if you have the flash controlled only by secure. Non-secure definitely cannot access the flash and not update any things during the flow. That is the only catch over here. I agree, like somebody can go with this flow, but yeah, this flow will be little bit, means you may get some malicious attacks for sure, because if you update and then you cannot guarantee anything may be running along with the update, then it may corrupt the banks also, and any external attacks may happen. Then it will, because this flash is completely accessible, and then while you are updating, somebody overwrite those feeds, then this update will not be helpful at all.
Oh, sorry. What I mean is when you reboot, you basically cut off all the connection to the outside world. So it's a very secure environment before you are linked to the outside world, right? So if you are actually before OS, it's very secure world already. No, doesn't matter if in the secure world or non-secure world. The whole environment is secure. That's what I mean. And you usually is when you boot, you got your flash lock, right? And it's not updatable, and then you reboot, and then you can unlock the flash. Yeah.
And this is, I think, we are talking very ideal situation where we have, but we are thinking there may some attack happen still if we do everything correctly in the software. And with the secure flash present in the secure world side, the attempt is to reduce such kind of attacks. I agree with you, like to little extent, yeah, it is already the secure environment, but we don't know, considering the flash is accessible by everybody. Does that make sense?
So just to let everyone know, we're overrunning a little bit. Oops, slight typo in the chat. The full recording will be made available on trustedfirmware.org for folks who happen to drop off. But yeah, I mean, while anybody's willing to talk or questions, I'm happy to keep the session open. I think a lot of people are dropping off now, Manish anyway, but any more questions for Manish, for the folks that are left? No, okay. Thank you, everyone. As I said, the recording may not be tomorrow, but hopefully by early next week, the recording will be available. And thank you, Manish, for presenting.
Thank you.
Thank you.
Thank you, Manish.
Thank you. Bye.
Bye.